Question 10 on our homework is a real good one. So we've got an object of m that goes and collides with an object of 2m because this thing is traveling with some speed v. And then these two things combine to one object that then has a mass of 3m. And then this 3m thing slides across the table until it reaches a speed of 0. And we want to know how far that thing goes. So really this is a great problem because it's really a combination of conservation of momentum and a combination of conservation of energy with friction doing work on the object. So what we have is on the back end here, friction is doing work on this object, and on the front end we have a collision where these two things collide. And we have that collide, therefore we have conservation of momentum. So we start this thing, the distance traveled here is going to be determined by the speed of this thing when it originally starts. Well, where does the speed of this thing when it originally starts come from? It comes from here. So we have a situation where conservation of momentum over here, the momentum of this situation, provides the energy for the thing to slide along. So the momentum of m plus the momentum of 2m equals the momentum of m after plus the momentum of 2m after. Well, this thing is stationary to start with, so that's 0. This is m times v plus 0 equals m times v prime plus 2m times v prime. But that v prime is the same because they combine. So in reality here, on the right side, I've got 3m times v prime, m times my original v. So therefore, the speed after the collision is a third of what it was to begin with. Now there's two ways to do the second part. If you look online, I post the answers, and I do it using kinematics and forces. But in reality here, it's a conservation of energy in a work done by friction problem. So this thing right here, once it gets going, has a certain amount of energy. I'm going to call that the initial energy, right? And then at any particular location, it's got a final energy. But because there's friction, those two things are not equal to each other. If I want them to equal each other, I've got to add the work done by friction over here. So in essence, we have this sentence right here. I'm gonna tighten it up, and I'm also gonna say, well, the type of energy we're talking about here is kinetic energy initially because the object is moving. Now that kinetic energy is all gone, so the final energy of that thing is 0. So whatever the initial kinetic energy is, well, that's equal to the work that's done by friction during the duration of this delta x. So, what's the kinetic energy of this 3m object? It's 1/2 times its mass times v prime, which is this velocity. So equals mu times, what's the work done by friction? Well, it's the friction force, which is mu times the normal force times delta x. Well, what's the normal force? In this particular case, it's the weight of the object. 1/2 m times v prime equals mu times m times g times delta x. Now look at this m right here. That's a generic m, standing for mass of the object. In this particular case, it has a value of 3 m's. Now, that being said, it doesn't really matter because it cancels off of each of those sides. So 1/2 v prime, whether it was equal to 3m or 9m, it doesn't matter, equals mu times g times delta x. So then v prime over 2 mu g is equal to delta x. But what's v prime in terms of the original v? V over 3. So that's, oops, my bad. All these should be squared. My bad. It's v prime squared. So v over 3 squared divided by 2 mu g. So delta x is equal to, well, v over 3 squared is v over 9, or v squared over 9 rather. That 9 pops down, and on the bottom we got 9 times 2. So that's v squared divided by 18 mu times g as our answer. Again, you could do that using force and kinematics equations, but I think in terms of what we are here for, the idea of it being done with work and energy is probably better.